breaking developments from the far reaches of our solar system. 3. An Atlas is no longer behaving like any ordinary comet. Just days ago, astronomers watched this strange interstellar body sweep within 2 astronomical units of the Sun, and what they saw defied every forecast. Instead of following predictions, its brightness surged far higher than expected. Its coma, its thin, glowing atmosphere, has expanded to nearly half the diameter of the Sun itself. Its light has taken on an eerie green tint, and strangest of all, its tail now appears to stretch toward the Sun instead of away from it, a phenomenon that by all conventional physics should be impossible. Now, as it speeds toward Mars at astonishing velocity, researchers admit they have no clear explanation. The countdown to perihelion has begun, and with every passing hour, this alien traveler looks less like a comet and more like a puzzle carved into the sky. Stay with me until the end of tonight's deep dive, because we're about to uncover what this breaking discovery means for everything we thought we knew, and what happens when alien chemistry awakens for the very first time under our Sun. Part 1. It's growing bigger, brighter, and strange. The numbers cannot be ignored, even when they seem impossible. In mid-September 2025, teams monitoring 3I Atlas began noticing something unnerving in their data streams. Brightness readings were climbing sharply, breaking away from the predicted curve. Instead of hovering around the expected magnitude of 15 or 16, the comet had jumped to 12, then 14. For anyone not fluent in astronomy's odd magnitude system, here's the catch. The lower the number, the brighter the object. A drop of just 2 magnitudes doesn't sound like much, but it means the object is suddenly producing about 6 times the light astronomers thought it should. And this wasn't a slow rise, it was accelerating. The COBS network, the Comet Observation Database, trusted by professionals and amateurs alike, quickly lit up with data showing Atlas brightening far beyond the normal warming curve. Earth-based telescopes confirmed the trend. This comet was now radiating more light than any model had projected. The tipping point came when Atlas moved inside 2 astronomical units of the Sun. To put that into context, 1 AU is the Earth-Sun distance, roughly 93 million miles. At 2 AU, Atlas was still twice as far from the Sun as we are, but something fundamental shifted at that point. Its brightening was no longer just unusual, it was alarming. So what could cause such a rapid surge in luminosity? The leading explanation points to volatile ices deep in its nucleus, frozen water, carbon dioxide, and stranger compounds, trapped since the object's birth around another star. As sunlight hits, these ices don't merely melt, they flash directly into gas, carrying dust with them, inflating vast reflective clouds around the nucleus. But here's the red flag: rapid brightening often means instability. Comets that outgas this violently can break apart, producing multiple fragments or massive debris fields. Others quickly burn through their volatile stores, fading just as suddenly as they flare. The fact that Atlas is brightening faster than anyone predicted means we may be witnessing unfamiliar processes scientists have yet to decode. And yet there's no need for impact fears. NASA confirms Atlas will never come closer than 1.8 AU from Earth, nearly twice our distance from the Sun. So the concern isn't collision, it's comprehension. What exactly are we watching unfold? Atlas is not just another icy rock from the Oort cloud, it is a time capsule from another solar system entirely, born around a different star, composed of materials untouched by our Sun's warmth. It's only now, perhaps for the first time in billions of years, feeling the heat of a star's inner system. This sudden brightening might represent dormant chemistry waking after eons of deep space slumber. Imagine exotic ices that were stable in the black cold of interstellar space now, for the very first time, sublimating into gases beneath our Sun's radiation. If true, we are glimpsing pristine chemical signatures carried across light years, preserved since the dawn of another system. And the clock is ticking. October 3rd will bring its closest approach to Mars, just 30 million kilometers. That's close enough for spacecraft orbiting the red planet to see details invisible from Earth. Then by October 29th and 30th, Atlas will reach perihelion, its nearest point to the Sun, at about 1.36 to 1. From early October through early November, ground-based observers will be blind to it. Astronomers call this period superior conjunction, when the Sun's brilliance drowns out everything nearby. That means Atlas's peak activity, its most dramatic revelations, will be hidden from Earth-based eyes. Only spacecraft scattered across the solar system, particularly those at Mars, may capture the show. All signs suggest Atlas will not pass perihelion quietly. Current data hints at mounting energy, perhaps even explosive outbursts, that could expose new clues about its composition and structure. But will those clues appear just as Earth's telescopes are blinded? What's clear is this: Atlas is transforming before our eyes. September's brightness data shows it drifting away from every prediction. It's becoming something altogether different from what it was on its long interstellar journey. The real question is, are we simply seeing an exotic version of normal comet activity, or something unprecedented, an entirely new category of celestial behavior we've never seen before? In the next part, we'll dive into its bizarre coma, why its tail seems to defy physics, and why its ghostly green glow may be our first glimpse of alien chemistry in action. But before that, let's take a step back, because 3I Atlas isn't just another comet. This is only the third interstellar visitor humanity has ever confirmed, and already it's rewriting the rule. 3I Atlas is moving at a pace more than double the orbital speed of our own planet Earth. These staggering numbers are not just trivia, they reveal the deeper mechanics of how interstellar bodies traverse the galaxy. Native objects within our solar system earn their velocity gradually, sculpted over billions of years by repeated gravitational interactions with the Sun and planets. By contrast, 3I Atlas is carrying momentum gained from its eons-long voyage between stars. Every kilometer per second in its motion represents untold stretches of distance crossed under the pull of different stellar systems and even the broader rotation of the Milky Way itself. Its current path draws it close to the ecliptic plane, the broad, flat disk where most of our planets orbit. This orientation is not random, it's what allows Atlas to sweep close to Mars now and line up for a more distant interaction with Jupiter in 2026. For something arriving from interstellar space, such a fortuitous trajectory is astonishing. If it had approached from a truly arbitrary angle in three-dimensional space, the odds of it brushing near multiple planets would have been vanishingly small. When 3I Atlas was first discovered, some scientists raised alarm. Its size and velocity briefly led to it being tagged as a potentially hazardous object, but continued tracking quickly removed that fear. At its closest, it will remain about 1.8 astronomical units from Earth, nearly twice our distance from the Sun. NASA confirmed this separation, allowing astronomers to set aside worries about planetary defense and focus instead on the scientific opportunity unfolding before us. Yet the true obstacle is not safety, but visibility. From early October into early November, Atlas undergoes what astronomers call superior conjunction. During this period, its apparent position in the sky lies so close to the Sun that even the best telescopes cannot separate its faint light from the blinding glare. Solar elongation, the angular distance between the comet and the Sun, as seen from Earth, drops below 30 degrees. To picture the challenge, imagine trying to pick out the glow of a firefly hovering beside a stadium floodlight. It is a natural limitation of ground-based astronomy that no amount of technology can overcome, and therein lies the irony. Just as Atlas experiences maximum solar heating, the very moment when its ices might sublimate most violently, when jets could erupt, when its tail might stretch to spectacular scales, Earth's observers will be forced into blind. The weeks of possible fragmentation, dramatic outgassing, and maximum tail expansion will happen precisely when human eyes on the ground cannot watch. This gap places extraordinary importance on the robotic explorers already stationed in space. Mars becomes a front-row seat to history. Orbiters like ESA's Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, will serve as humanity's best vantage points during this blackout. For once, the responsibility of monitoring a cosmic visitor does not rest with Earth, but with machines orbiting another world. What happens after perihelion is a matter of cautious optimism. Should Atlas survive its close solar pass intact, Earth-based telescopes will regain the ability to track it from November onward as its angular separation from the Sun increases. But there is a catch. By then, the comet may already be fading, its most volatile ices burned away. Predictions suggest its peak brightness will only reach magnitude 11 or 12, too dim for unaided human eyes, but within reach of small telescopes. For casual stargazers, it may never rival the dazzling naked-eye comets of the past. For scientists, however, that lack of spectacle doesn't lessen its importance. The velocity curve of Atlas adds another wrinkle. As it plunges toward perihelion, solar gravity accelerates it further, increasing both its speed and the violence of heat. After perihelion, the same gravity well begins to slow its retreat, stretching the timeline during which spacecraft at Mars can continue observations. Then in March 2026, calculations project a distant pass near Jupiter. Though not nearly as close as its brush with Mars, this encounter could provide further observation opportunities as the comet begins its final journey outward. This timeline underscores the uniqueness of the event. Unlike periodic comets, which return again and again for study, 3I Atlas is a once-only visitor. It will never come back. Every observation must be captured now, during this singular pass through our solar system. That means the narrow window, the inconvenient conjunction, and the reliance on spacecraft all combine into a scientific challenge, unlike any faced before. The cosmos has set the schedule, and all we can do is race to keep up. Part 4, the coma expansion and structure. What may be the most astonishing revelation about 3I Atlas is not its interstellar origin or its rare trajectory, but the sheer impossible scale of the atmosphere it is building around itself. In September 2025, NASA's Sparks telescope returned data that shocked the cometary science community. Atlas was generating a carbon dioxide-dominated coma, stretching nearly 338,000 kilometers from its core. To put that in perspective, this faint shroud now spans half the diameter of our Sun. Within that bubble, the entire orbit of Mercury could fit comfortably. For comparison, most comets in our system produce comae far smaller than this. What Atlas is displaying is nothing short of unprecedented. A comet's coma forms when solar radiation heats the frozen materials locked in its nucleus, causing them to sublimate directly into gas and drag dust outward. The standard analogy likens a comet to snowball steaming under sunlight. But this simple picture barely captures the ferocity of what's happening here. In Atlas' case, the outgassing is so violent that it has created an atmosphere of a size and density never before measured. The composition of this coma deepens the mystery. Unlike most comets in our solar system, where water vapor dominates, Atlas' envelope is rich in carbon dioxide. This inversion suggests that the comet formed in a zone where CO2 could condense while water largely remained vapor. Perhaps in the frigid outer reaches of another star's protoplanetary disk, temperatures dipped so low that carbon dioxide became the primary volatile, with water relegated to a supporting role. In short, Atlas chemistry points to conditions very unlike those that shaped our local comet. But the size and chemistry are only part of the puzzle. Images from Hubble and ground observatories have revealed structures that defy traditional comet physics. Instead of the familiar tail pointing away from the Sun, Atlas has sprouted an anti-tail, a luminous plume that seems to aim back toward the Sun itself. Conventional models dictate that solar radiation pressure pushes dust and gas outward, away from the star. Yet here, the geometry appears reversed. In July 2025, Hubble captured what scientists described as a forward-pointing glow, a fan-shaped spray of material heading sunward. Gemini South confirmed the same phenomenon in August, and this was no passing quirk. The structure persisted for weeks, hinting at something fundamental at play. Theories abound. Large, heavy dust grains, too massive to be pushed easily by solar photons, could maintain such trajectories if ejected forcefully from the nucleus. Alternatively, projection effects from Earth's vantage point might make dust streams appear to angle sunward, even if their true motion is more conventional. But neither explanation fully satisfies the data. The persistence, clarity, and scale of the anti-tail strain the limits of current models. One possibility is that Atlas' nucleus rotates in a peculiar way, creating temperature extremes between its day and night sides that funnel out gassing preferentially in certain directions. Another is that the interstellar ices themselves respond to sunlight differently than anything seen before, producing jets that break our expectations. Spectroscopic readings show coma gas racing outward at velocities higher than typical comet. Infrared sensors measure elevated temperatures that suggest additional heating mechanisms beyond sunlight alone, perhaps chemical reactions between unusual compounds, or trapped energy releasing from exotic ice structures forged in interstellar cold. Three-dimensional reconstructions of the coma display marked asymmetry, with jets and fans erupting from specific regions. This implies that its nucleus is patchy, with discrete volatile-rich areas exposed by impacts or long-term erosion during its deep space journey. In essence, Atlas' surface is not uniform, but a patchwork of chemical zones recording its birth conditions and evolution. Dust measurements within the coma further complicate the story. To generate such a stable anti-tail, Atlas must be producing unusually large grain. This hints either at an original dust-to-ice ratio, very different from solar system comets, or at modifications sustained during its interstellar passage. All of this makes modeling its future incredibly difficult. Standard cometary equations cannot account for the outgassing rates, the CO2 dominance, or the anti-tail geometry. Researchers are forced to adapt, rewriting comet physics on the fly. The implications reach beyond Atlas. If interstellar comets consistently display such exotic features, our picture of comets, based only on our solar system's examples, may be woefully incomplete. Each visitor from the stars could carry entirely new rules of behavior. And just as Atlas' coma continues to expand, so too does the scope of the questions it forces us to ask. Yet even this massive shroud of gas and dust was soon outshined by another transformation. In mid-September, 3I Atlas underwent a change so visually dramatic that it stunned astronomers worldwide. The entire comet began to glow a vivid, almost ghostly green. Part 5, The Green Glow. In September 2025, something extraordinary happened. Practically overnight, 3I Atlas shifted from a dim, pale blur into an emerald beacon unlike any other comet we've seen. Sensitive cameras detected the hue first, noting a sharp green radiance enveloping the nucleus. The effect became undeniable during the lunar eclipse of September 14th, when darker skies amplified the contrast. Against the shadowed dome of space, the comet seemed alive, radiating color as though lit from within. This transformation is not merely cosmetic. The green emission tells a story written in quantum terms. Certain molecules, when struck by ultraviolet sunlight, leap into excited states. As their electrons fall back to normal, they release photons of precise wavelengths our eyes perceive as glowing green. For Atlas, the prime suspect is diatomic carbon, C2 molecules made of two carbon atoms, bonded together. These molecules act like neon signs floating in space. When energized, they fluoresce at about 516 nanometers, producing the emerald glow that has become Atlas' new hallmark. But here's the strange part. Initial spectroscopy of Atlas suggested only modest amounts of carbon-bearing compounds. Instead, its chemistry seemed dominated by water and carbon dioxide. So why is its coma suddenly saturated with green? What processes are freeing enough C2 to flood the atmosphere with emerald light? That question is now driving a fresh wave of investigation. This puzzling mismatch between the vivid green radiance captured in telescope images and the measured chemistry of the comet's atmosphere has left astronomers racing to untangle what's truly unfolding within 3I Atlas. One leading theory points to a shift in its outgassing dynamics. As the comet crossed the 2 astronomical unit mark in early September, the intensifying solar heat may have unlocked hidden carbon-rich deposits deep within the nucleus. These reservoirs, shielded for millions of years during its cold passage through interstellar space, could now be exposed to solar energy for the very first time. The timing of the comet's emerald transformation coincides almost perfectly with its sudden surge in brightness during mid-September. That synchronicity suggests both phenomena may share the same root cause, perhaps a violent release of buried volatiles that not only amplified its brightness but also ignited the chemistry responsible for the comet's eerie glow. Other interpretations suggest the explanation might not rest solely on simple diatomic carbon fluorescence. Comets can carry dozens of different carbon-based compounds, each capable of producing distinctive spectral emission. It's possible that the green halo stems from a blend of these molecules, or even from exotic carbon-bearing compounds unique to interstellar objects that rarely, if ever, appear in local comets. To complicate matters further, telescope design and image processing methods can influence how colors appear. Different filters and calibration techniques can make the comet's glow look emerald in one dataset, yet teal or yellow-green in another. These variances highlight the challenges of interpreting a phenomenon this faint and complex. The evolving nature of the glow provides another crucial clue. Instead of a steady, uniform emission, observers have reported patchiness, regions of the coma shining more vividly green than others. This uneven distribution implies that carbon-bearing gases may be released in bursts from localized vents on the comet's surface, rather than spreading evenly. Alternatively, the irregular glow could result from solar ultraviolet light breaking apart more complex organics into simpler fragments that then fluoresce. Either way, the green emission acts as a diagnostic signal. Its strength and spread depend on gas density, molecular temperature, and the intensity of incoming solar UV radiation. By mapping how the glow changes over distance and time, astronomers can probe the density, temperature, and structure of 3I Atlas's evolving atmosphere. Temperature readings derived from the fluorescent signature suggest that the carbon compounds within the coma are in thermal balance with surrounding gases. This implies efficient energy exchange and frequent molecular collisions, valuable information about the physical behavior of gases expanding into space. In a broader sense, 3I Atlas's emerald shroud underscores just how different interstellar visitors can be. Oumuamua, the first such object detected, showed no comet-like activity at all. Borisov, the second, exhibited a more familiar bluish-white appearance caused by scattered sunlight rather than bright molecular emission. But 3I Atlas is rewriting the rulebook by producing a vivid green coma, a trait long associated with classical solar system comets, yet likely driven by chemical compositions alien to our neighborhood. The timing of this color shift couldn't be more critical or more frustrating. As the comet edges Kayses to Superior Conjunction in early October, Earth-based telescopes will lose their view just when the glow could intensify or morph into something entirely new. Historically, the peak of molecular fluorescence often coincides with perihelion, when sunlight is most intense. Unfortunately, that window will occur while 3I Atlas is effectively invisible from Earth. Astronomers are now in a race against time, with every clear night in late September and early October representing an invaluable opportunity to capture spectra and pinpoint the molecules responsible before the comet vanishes into solar glare. Large telescopes with sensitive spectrographs are essential, yet observing conditions grow more hostile with each passing day. Beyond its visual beauty, the green aura carries profound scientific meaning. It signals that 3I Atlas is undergoing deep chemical transformations triggered by its encounter with the Sun. Molecules that had remained inert for eons, frozen since the comet's birth in another star's nursery, are now awakening. For the first time in perhaps billions of years, alien chemistry is revealing itself. Materials forged under conditions far beyond our solar system are now fluorescing in space, visible to human eye. The glow is more than an astronomical curiosity. It's a once-in-history glimpse into the activation of primordial chemistry from another world. Yet this awakening highlights the limits of our current tool. As Earth loses sight of the comet during its most dramatic stage, humanity will have to rely on space-based instruments scattered across the solar system to continue tracking this unprecedented event. And just as the glow fades from terrestrial view, the broader challenge of observing 3I Atlas enters its next phase. Part 6: The Obstacles of Observation. The cosmos often seems to conspire against astronomers, and 3I Atlas is no exception. Right as this comet reveals its strangest behaviors, the explosive brightening, the gargantuan coma, the mysterious green halo, the rules of orbital geometry intervene to conceal it. Even the most advanced instruments ever built face the same unyielding problem as small backyard telescopes. No one can observe what lies behind the blinding glare of the Sun. As the comet accelerates toward perihelion, its position relative to Earth drifts closer to the Sun's line of sight. Soon solar brilliance will overwhelm its faint glow, making meaningful observation nearly impossible. The James Webb Space Telescope did manage a crucial spectroscopic capture on August 6, recording chemical fingerprints with its powerful near-infrared instrument. These data offered rare insights into 3I Atlas's makeup during one of the few safe alignment windows when pointing Webb toward the comet didn't risk exposure to solar radiation. But those results came before the September upheaval, before the green glow and rapid brightening turned Atlas from curious into extraordinary. The Hubble Space Telescope also contributed critical imagery in late July, documenting the strange sunward plume structure and constraining the size of the nucleus. Since then, however, high-resolution updates from space observatories have become rare. Ironically, the very instruments most capable of decoding the comet's mysteries, Hubble, Webb, and other orbital telescopes, are bound by strict safety rules that forbid them from pointing too close to the Sun. And now, as the geometry worsens, those restrictions cut off exactly the kind of coverage scientists crave. On the ground, astronomers face another tangle of difficulty. Different observatories report varying brightness values due to differences in filters, calibration, and atmospheric conditions. This scatter isn't unusual in comet science, but in Atlas's case, it complicates an already challenging analysis. The Comet Observation Database aggregates global reports, showing the comet consistently brighter than predicted models throughout September. Yet individual discrepancies remain wide, reflecting both measurement uncertainties and the comet's unpredictable nature. Amateur astronomers play a surprisingly important role here. While their smaller telescopes lack the precision of major facilities, they provide continuous coverage over long periods, filling gaps professionals can. But their contributions also carry added noise, atmospheric turbulence, light pollution, and equipment quirks. Collectively, these reports show Atlas defying predictions and brightening faster than expected. Whether this reflects outbursts, structural changes, or model errors remains unclear. The core limiting factor is solar elongation, the angular separation between the comet and the Sun. Once that shrinks below 30°, even the largest observatories struggle. Below 20°, most professional monitoring stops altogether, and amateurs lose track well before that. That countdown began in early October, and by mid-month, Atlas will effectively disappear into daylight. The cruel irony is unmistakable. At the very moment when maximum outgassing, tail growth, and possible breakups are expected, humanity will be blind. Data reduction adds yet another challenge. Isolating the comet's light from background stars, cosmic interference, and instrumental noise requires painstaking processing. As Atlas fades into the Sun's glare, the margin for error grows razor-thin. Spectroscopy, the key to identifying molecular composition, demands strong signals and dark skies. Both are vanishing as the comet sinks into the solar horizon. Atmospheric physics adds its own constraint. Earth's atmosphere scatters short wavelengths like ultraviolet more strongly than red light, the same process that makes our sky appear blue. Unfortunately, many vital molecular emissions from the comet occur in this hard-to-detect UV range, making them increasingly inaccessible as elongation drops. This is why international cooperation becomes critical. Observatories spread across hemispheres and time zones must synchronize efforts, squeezing out every possible observation before Atlas slips away. Southern observatories may retain slightly better viewing geometry than northern ones, offering brief extensions of visibility if coordinated properly. But even if data collection continues, interpreting it remains a thorny problem. The comet's brightness spike may reflect genuine outbursts, or simply reveal flaws in the predictive models used. Sorting between those possibilities requires continuous long-term monitoring, something Earth will soon no longer be able to provide. Weather compounds the urgency. Cloud cover, storms, and poor seasonal conditions can rob astronomers of irreplaceable nights of data. Unlike returning comets, Atlas will never pass this way again. Each missed observation is lost forever. Ultimately, the shift is unavoidable. As Earth-based telescopes go blind, the task of watching 3I Atlas passes to the robotic eyes scattered across the solar system. Mars-orbiting spacecraft, built for entirely different missions, are now poised to become humanity's frontline observers of this extraordinary interstellar traveler. Behind the polished language of peer-reviewed journals and the deliberately cautious phrasing in astronomical bulletins, a wave of both excitement and unease is spreading through the international community of comet specialists. 3i Atlas is not acting according to the predictable patterns outlined by decades of cometary research, and scientists are beginning to concede, albeit in their typically reserved fashion, that they may be witnessing something unlike anything observed before. The global brightness data paints a troublingly consistent picture. Independent monitoring networks, ranging from the official Comet Observation Database to organized amateur efforts, have all confirmed the same disquieting reality. 3i Atlas is shining far more intensely than existing cometary models predict. The deviation isn't minor, it's several magnitudes above forecast, far outside the margins typically dismissed as random error or instrument noise. Matthew Knight, a comet researcher whose career has been devoted to understanding how these frozen relics evolve under solar influence, highlighted just how unusual this event is. In a recent interview, he explained that the September surge in luminosity challenges fundamental assumptions about how volatile ices are released. The acceleration of this brightening, he noted, seems to be happening on timescales vastly quicker than those allowed for in standard thermal models. Such uncertainty sparks a rare kind of enthusiasm among scientists. The awareness that they may be observing a phenomenon that forces entirely new theoretical frameworks. Publications like Earth's Skies have picked up on this tension, noting how each fresh observation continues to puzzle researchers, while acknowledging that much of what appears strange could simply be the unpredictability of matter forged in alien stellar nursery. One especially baffling feature is the comet's forward-facing plume. While anti-tails and sunward jets are known in cometary science, the persistence and strength of 3i Atlas's jets stretch existing models to their breaking point. In response, researchers are entertaining increasingly unconventional possibilities: non-standard dust grain sizes, irregular spin states, or even exotic mixtures of volatiles that break the rules of textbook comet physics. There is, however, no debate over one fact: 3i Atlas is showing activity levels well above those of typical comets at equivalent distances from the Sun. Observations from NASA's SphereX mission revealed a carbon dioxide-dominated coma that extends farther than theory would ever predict, implying gas release rates that dwarf ordinary models. This is not a subtle discrepancy, it's a striking departure that demands explanation. At the same time, astronomers remain mindful of a known pitfall in comet studies: outburst bias. Many comets undergo sudden flare-ups of activity, producing temporary surges in brightness that can be mistaken for long-term trends. The question tormenting researchers now is whether the September outburst signals a sustained deviation in behavior or merely a fleeting spike destined to fade. This dilemma is made worse by timing. The crucial period when solar heating peaks near perihelion, likely to be the moment of greatest activity, will occur while 3i Atlas is positioned too close to the Sun for Earth-based telescopes to monitor. If its most dramatic changes happen then, astronomers may be left permanently in the dark. Dr. Kerry Holt of the European Southern Observatory, who specializes in interstellar visitors, captured the collective frustration by calling this a cosmic conspiracy against understanding. The exact moment when the comet might reveal its most profound secrets is also the moment Earth-bound observers are effectively blinded by solar glare. Beyond brightness, the object's very identity is under debate. Spectroscopic data suggests a chemical mixture with carbon dioxide to water ratios, unlike those seen in our own solar system. This could reflect drastically different conditions in its birth environment, or chemical alterations accumulated over eons of drifting between stars. Amateur astronomers play a vital supporting role, filling observational gaps that large facilities cannot cover. Yet their diverse instruments and methods lead to scatter in brightness reports, complicating efforts to distinguish real variability. Agencies like the European Space Agency's Space Situational Awareness Program attempt to harmonize these reports, confirming the overall trend of anomalous brightening, while admitting to difficulties in quantifying just how extreme the deviation really is. Meanwhile, the mood within the scientific community on social platforms is telling. Researchers cautiously share images and preliminary numbers, often accompanied by disclaimers about their uncertainty. The tone is one of restrained excitement, acknowledging that something remarkable is unfolding, but resisting the urge to draw hasty conclusions. The peculiar green hue observed in mid-September adds to the puzzle. While diatomic carbon fluorescence can account for much of the glow, the intensity and timing don't perfectly align with chemical signatures gathered earlier. This mismatch hints at either instrumental limitations, or more intriguingly, chemical processes far more complex than current models assume. Anticipation is now building toward upcoming conferences, particularly the American Astronomical Society's Division for Planetary Sciences meeting, where no fewer than half a dozen talks will focus on 3I. Research teams across the globe are urgently reworking models to explain not just what the comet is doing, but why their predictions continue to fail. The urgency stems from more than curiosity. It's about seizing a rare, perhaps once-in-a-lifetime, scientific opportunity. Humanity has officially confirmed only 3 interstellar visitors. Each carries irreplaceable information about conditions beyond our star system and the chemistry of planet-building materials in distant stellar neighborhoods. With Earth's view slipping away, international cooperation has ramped up. Observatories in Hawaii, Chile, Spain, and Australia are synchronizing efforts to extract as much information as possible before conjunction cuts them off. Every facility brings unique strengths, some excelling at high-resolution imaging, others at dissecting faint spectra. Another layer of complexity lies in communication with the public. Media outlets sometimes overhype preliminary findings or present speculative interpretations as certainty. Researchers are walking a careful line, wanting to share the thrill of discovery without exaggerating conclusions that remain uncertain. The implications ripple further. While 3I Atlas poses no danger to Earth, its erratic behavior underscores blind spots in our predictive model. If we cannot fully explain this comet's response to solar heating, what does that say about our ability to anticipate the behavior of other, potentially hazardous bodies? Ultimately, the growing sense of alarm is rooted in something fundamental, the realization that nature repeatedly produces surprises far stranger than our theories allow. With October fast approaching and visibility slipping away, astronomers are pinning their hopes on spacecraft scattered throughout the solar system to catch the revelations Earth-based telescopes will miss. Part 8 now shifts focus to one such opportunity, a historic close pass by Mars that could offer an unparalleled vantage point. As 3I Atlas approaches perihelion, the deep internal heating of its nucleus may release previously hidden chemical species, potentially detectable for the first time through spectroscopic measurements. Observers could witness color variations beyond the familiar green glow already noted as new molecular compounds begin fluorescing under the sun's ultraviolet irradiation. If complex organics exist within the comet, they may break down into simpler fragments that emit light across multiple wavelengths, creating a vivid spectrum of visible emission. The antitail, a feature that has long fascinated astronomers, may undergo significant transformation as perihelion draws near. Heightened dust ejection could generate multiple tail structures pointing in different directions, as particles of varying sizes respond differently to radiation pressure. This evolving geometry can offer key insights into the nucleus's rotation, surface composition, and interior structure. The analysis of dust grains becomes especially critical during this phase. The size distribution and chemical makeup of particles expelled from the nucleus reveal much about its formation and internal makeup. Large grains may indicate a loosely bound interior with voids, while fine dust could reflect a more compact structure or specific chemical processes that favor smaller particles. Meanwhile, the magnetic and plasma environment near the sun adds another layer of complexity. The solar wind streams of charged particles flowing from the sun interacts with ionized gases in the coma, producing intricate electromagnetic. These interactions can accelerate particles to high speeds, produce visible glows in the surrounding gases, and shape plasma tails that stretch millions of kilometers behind the nucleus. If spacecraft can obtain temperature measurements, they may uncover fundamental insights into the thermal properties of 3I Atlas and its internal structure. Different volatile compounds sublimate at characteristic temperatures, effectively providing a chemical thermometer for understanding the heating process. Solar radiation penetrates the nucleus's surface layers, and the aftermath of perihelion depends largely on the quantity of volatiles present and how efficiently they can escape. A comet with abundant volatile material could remain highly active for weeks or even months after perihelion, whereas an object with limited reserves might fade quickly as its surface depletes. Gravitational influences from the Sun's intense field near perihelion could also subtly modify the comet's future trajectory. While 3I Atlas will continue outward along its hyperbolic path, even slight velocity changes may affect the timing and geometry of its encounters with outer planets such as Jupiter. Perihelion marks the apex of 3I Atlas's solar system passage, the moment when billions of years of interstellar evolution meet the extreme radiation of our star. The encounter could produce dazzling displays of outgassing and dust jets, or it might quietly reshape the nucleus and coma in ways hidden from view. Astronomers are left to wonder whether the comet will emerge recognizable as it was in September, or transformed into a fundamentally different object, its secrets concealed behind the sun's blinding glare, until orbital mechanics allow Earthbound observers to glimpse the result. To contextualize 3I Atlas, we look back at the brief but remarkable history of confirmed interstellar objects. Only 2 visitors preceding it have been definitively identified as extrasolar, each challenging astronomers' expectations. Their stories underscore the diversity of objects wandering the galaxy and illustrate how these visitors defy simple categorization. The first, Oumuamua, was discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. Initially catalogued as an asteroid due to the absence of a detectable coma, Oumuamua defied all expectations. Its highly elongated shape, roughly 400 meters long and 40 meters wide, had no counterpart in the solar system. Even more puzzling was its non-gravitational acceleration as it moved away from the sun, an effect inconsistent with gravity alone. The cause remains debated: minute outgassing, radiation pressure acting on its unusual shape, or perhaps more exotic physics beyond our current model. The lack of a visible coma suggested minimal volatiles, yet forces were clearly acting to accelerate the object. 2 years later, 2IA Borisov appeared on August 30, 2019, discovered by amateur astronomer Gennady Borisov in Crimea. Borisov initially seemed ordinary, a classical comet with a fuzzy coma and tail structures matching expectations for solar-heated, icy bodies. Yet spectral analysis revealed an unusual chemical composition. Its carbon monoxide content was far higher than typical solar system comets, hinting at formation in a protoplanetary disk with different thermal and chemical conditions. The dust-to-gas ratio also differed, suggesting distinct formation or evolutionary process. Borisov offered the first concrete evidence that other star systems produce comets with fundamentally different compositions. Now 3I Atlas joins this rarefied company, and in comparison, its features appear extraordinary. The carbon dioxide-rich coma detected by SphereX and confirmed through follow-ups represents the most extreme compositional departure yet observed among interstellar visitors. JWST analyses indicate CO2 dominance over water vapor at unprecedented ratios, implying an even more exotic formation environment than Borisov. The sunward-pointing anti-tail is entirely unique, defying previously observed comet physics. While Oumuamua had no visible tail and Borisov exhibited conventional solar-driven tails, 3I Atlas's tail geometry challenges centuries of cometary understanding. Its rapid brightening in September adds further anomaly signaling active processes, outgassing, structural shifts, or surface evolution, operating over timescales far shorter than those of previous interstellar objects. Size estimates reveal further distinction. Oumuamua's elongated body measured roughly 400 by 40 meters, larger than small asteroids, but smaller than most active comet nuclei. Borisov's nucleus, about 1 kilometer in diameter, fell within the normal range for solar system comets. 3I Atlas's size is more ambiguous. Hubble observations suggest a diameter between 0.3 and 5.6 kilometers, reflecting both small and moderately large cometary scale. The difficulty lies in disentangling the nucleus from its extensive coma, a trait that sets it apart from prior interstellar visitors. Chemical analysis has advanced with each discovery. Oumuamua's brief visibility and lack of outgassing limited study to surface reflection and density estimate. Borisov's conventional comet behavior allowed detection of water, CO and other molecules. 3I Atlas, with state-of-the-art instruments like JWST, Hubble and next-generation ground-based spectrographs, offers the most detailed chemical, physical, and temporal data ever obtained from an interstellar object. Orbital characteristics also provide context about their galactic origin. Oumuamua approached from near Vega with a hyperbolic excess velocity of about 20. 3I Atlas surpasses both at approximately 39 kilometers, hinting at formation around a massive star or acceleration through multiple gravitational encounters across the Milky Way. This extreme velocity affects perihelion behavior, as higher speed limits solar heating penetration into the nucleus. The discovery intervals between interstellar visitors suggest their inner solar system passages are rare but recurring. 2 years separated Oumuamua and Borisov, followed by a 6-year gap before 3I. These objects are small, brief in visibility, and challenging to detect, yet they reveal a vast diversity of formation and ejection processes across star systems. Each one expands our understanding of the possibilities in interstellar small body population. 3I Atlas, with its unprecedented coma size, anti-tail chemistry, and rapid brightness changes, pushes these boundaries further. Its post-perihelion behavior may continue the pattern of surprising astronomers, revealing processes previously unimagined and reinforcing the lesson that galactic small body formation is far more varied than what solar system experience alone would suggest. The emerging narrative around 3I Atlas resembles a cosmic detective story. Evidence is hidden, forcing astronomers to hypothesize from incomplete clues until the comet emerges from solar glare. The size and shape of the nucleus remain debated. Hubble observations suggest 0.3, 5.6 kilometers, with uncertainties tied to separating the nucleus from the coma. Size affects mass, density, outgassing potential, and structural stability during perihelion. Different measurement approaches conflict. Infrared thermal modeling favors a small reflective nucleus, while visible light analysis suggests a larger, darker object. These discrepancies may stem from compositional variations, observational limits, or incomplete understanding of perihelion heating responses. Composition studies further complicate the picture. JWST spectroscopy confirms CO2 as the dominant volatile, with concentrations exceeding water vapor by wide margins, distinct from typical solar system comets. Yet the green hue observed in September, normally caused by diatomic carbon, does not naturally arise from CO2 outgassing. Either other chemical species were missed, or more complex processes are at work. Ground-based spectrographs have identified additional molecules, including cyanides and organics, pointing to chemical diversity beyond CO2 dominance. The anti-tail remains the most confounding feature. Standard comet physics predicts tails pointing away from the sun, driven by radiation pressure on gas and dust. 3I Atlas's tail geometry defies this principle, creating one of the most intriguing puzzles in recent observational astronomy.
3I Atlas appears to defy conventional cometary physics by ejecting material that forms structures oriented toward the sun rather than away from it.
Recent theoretical work by Dr. Keita and Dr. Lowe, currently undergoing peer review, suggests that this anti-tail may arise from unusual distributions of dust grain sizes combined with particular ejection patterns from the nucleus. Their models indicate that sufficiently large particles launched sunward with enough initial velocity can overcome the effects of solar radiation pressure, creating the observed forward-pointing formations. Other hypotheses propose alternative mechanisms. Some researchers point to electromagnetic interactions between charged dust grains and the solar magnetic field as a means to redirect material unexpectedly. Others suggest that asymmetries in the comet's temperature caused by its rotation might focus outgassing in specific directions independent of solar radiation forces. The rotation rate of 3I Atlas remains a mystery, despite months of observational attempts. Light curve studies, which track brightness changes as an irregularly shaped nucleus rotates, have failed to reveal consistent periodicity. This lack of a clear rotational signature could indicate very slow rotation, a near-spherical shape, or a complex rotation that obscures simple periodic behavior. Rotation profoundly affects cometary dynamics. Fast-spinning nuclei experience centrifugal effects that alter outgassing patterns and structural stability, while slow rotators develop pronounced day-night temperature gradients that concentrate volatile release in heated regions. The uncertainty in 3I Atlas's rotation complicates thermal modeling and predictions of its future behavior. The brightness surge noted in September adds further interpretive challenges. Multiple observation networks reported that 3I Atlas brightened well beyond theoretical expectations, though the magnitude of this increase remains contested. Some observers recorded changes of several magnitudes, while others reported more moderate variations within normal cometary limit. These discrepancies arise from measurement difficulties. The comet is near the detection thresholds of many telescopes. Photometry is complicated, and observers use differing reference stars, filters, and reduction techniques. The absence of baseline data for comparison further complicates analysis. Unlike periodic comets with multiple apparitions to study, 3I Atlas represents a single encounter, leaving researchers dependent on models based on solar system comets. Models that may not accurately describe interstellar objects. Studies of the comet's origin attempt to trace its galactic path backward to determine its likely birth environment. Current kinematic analysis places the object somewhere within the Milky Way's thin disk, the star-rich region where ongoing star formation occurs. Yet uncertainties in position and velocity compound over time, generating broad error ellipses that encompass multiple potential source regions. Understanding its galactic origin has implications for its composition and age. Objects ejected from young systems may carry different chemical signatures than those from older stars. The observed CO2 dominance could indicate formation in a protoplanetary disk with unique temperature and chemical gradients. Structural stability is another area of active debate. The extensive coma and anti-tail may reflect either a volatile rich nucleus or one undergoing physical disruption. Some researchers propose that 3I Atlas is a loosely bound rubble pile, a collection of smaller fragments held together weakly and prone to fragmentation under thermal or tidal stress. Other models treat it as a monolithic body with unusual surface or internal properties driving its observed activity. This distinction is critical for predicting perihelion behavior, where thermal and tidal forces peak. The two astronomical units switch-on observed in early September remains poorly understood. The sudden activity increase at this distance could signal the sublimation of volatiles with specific activation temperatures or reveal structural changes exposing previously buried ice. Different compounds sublimate at varying distances. Water begins outgassing significantly around 3 astronomical units, while CO2 can remain active far beyond that. 3I Atlas's behavior suggests a complex mix of volatiles that do not follow familiar solar system patterns. The observational gap during solar conjunction leaves major uncertainties about which models best explain its activity. Critical tests, including responses to maximum solar heating, fragmentation events, and evolving outgassing patterns, will occur largely hidden from Earth-based instruments. When the comet re-emerges in late November, researchers may either validate current theories or confront entirely new puzzles. These debates exemplify the challenge of studying rare interstellar phenomena at the edge of observational capabilities. Every measurement carries uncertainty. Every model involves assumptions, and interstellar objects may operate according to physical principles not yet encountered within the solar system. Before considering speculative possibilities, it is essential to exhaust natural, yet unusual explanation. While 3I Atlas behaves in ways unfamiliar to observers, it likely adheres to known physics, though under extreme conditions rarely seen. Its CO2-dominated coma provides the first clues to its alien behavior through conventional cometary science. This composition implies formation in a stellar region cold enough for CO2 to condense as ice, while water remained largely vapor, likely beyond the CO2 snowline, the distance from a star where carbon dioxide freezes. In the solar system, this line lies far from the region where most comets form, explaining why water typically dominates comet volatiles here. Other stellar systems may have different thermal or chemical profiles, placing the CO2 snowline closer to the star or favoring CO2 formation over water. Cooler stars or carbon-enriched compositions could produce CO2-rich comets in zones where water-rich bodies form in our system. This formation environment hypothesis also explains the comet's vigorous activity. CO2 sublimates more readily than water at comparable temperatures, potentially generating gas production rates far higher than water-dominated comets. This enhanced volatility may account for the rapid brightening in September and the unusually large coma observed by Sphere. Yet CO2 alone cannot explain the sunward-pointing anti-tail. Here, dusty plasma physics becomes relevant. Solar UV radiation ionizes gases in the coma, creating plasma that interacts with charged dust grains to produce self-organizing structures beyond predictions of gravity and radiation pressure alone. Streams, filaments, and even spirals can form as charged particles respond to solar wind magnetic fields, sometimes overriding radiation pressure and producing anti-tail formation. Enhanced outgassing in 3I Atlas strengthens these effects. Higher gas densities increase ionization, while its unusual chemistry may create molecular species more easily ionized. Rotation provides an additional natural explanation. A slowly rotating nucleus can develop strong day-night temperature contrasts, concentrating outgassing in certain regions. Thermal expansion and gas pressure from hot regions may eject material sunward with velocities sufficient to overcome radiation pressure. Interstellar objects may acquire unusual rotation rates due to collisions with dust, gravitational interactions with stars, or magnetic influences during interstellar travel. The green emission observed in September also admits natural explanation. While diatomic carbon typically produces such color, early spectroscopy showed little evidence for carbon-bearing molecules beyond C. A threshold effect may have triggered C2 formation once the comet reached 2 astronomical units, via photodissociation of CO2 into CO and O, followed by further processing to produce. Alternative explanations involve trace organics breaking down under solar radiation, releasing carbon fragments that fluoresce at green wavelengths. Variations in surface composition could also drive anomalous activity. The nucleus may host discrete regions, some CO2-rich, others water-dominated, and still others containing organics. As the comet nears the Sun, heating different regions activates distinct materials, producing changing outgassing patterns. Porosity and internal structure further influence behavior. A highly porous nucleus allows deep penetration of solar heat, activating subsurface volatiles normally insulated from surface temperatures. This enhanced porosity can explain both the large coma and rapid brightness changes. Interstellar processing, cosmic ray bombardment, dust collisions, or radiation exposure may also modify nucleus properties, influencing its perihelion behavior. The most plausible explanation for 3I Atlas's extraordinary activity combines multiple natural processes. CO2-rich composition drives intense outgassing, plasma physics produces anti-tail structures, slow rotation focuses activity regionally, and complex chemistry explains color changes. Each mechanism operates within conventional physics, yet their interactions under extreme conditions can create phenomena that seem impossible from a solar system perspective. 3I Atlas may be an exceptionally strange comet rather than a fundamentally alien object, but its uniqueness promises to transform our understanding of small body physics across the galaxy. We now enter a realm where science and imagination intersect, a zone in which the line between conventional natural processes and truly extraordinary possibilities begins to blur. While there is no credible evidence supporting any of these highly speculative interpretations of 3I Atlas's behavior, its unprecedented characteristics invite the sort of conjecture that has accompanied every puzzling astronomical discovery in human history. These notions exist not as serious scientific theories, but as intellectual exercises designed to highlight just how remarkable our interstellar visitor truly is. Among the most persistent of these exotic ideas is the alien technology beacon hypothesis. Ever since the discovery of Oumuamua ignited debates over artificial origins, each new interstellar object has spurred speculation regarding potential technological signatures. In this scenario, 3I Atlas's rapid brightening, unusual anti-tail, and massive coma could hypothetically represent activation sequences of a dormant probe engineered to respond to stellar radiation environments. This concept imagines the comet as a silent artifact, preserving its energy and structural integrity during its journey between star systems, only to awaken when solar radiation reaches levels sufficient to trigger pre-programmed systems. The September brightening might mark the initial activation, while the anti-tail could signify deliberate energy or material emissions, serving a technological function. However, this interpretation faces immediate challenges when compared to observational data. Spectroscopic analyses from the James Webb Space Telescope and ground-based instruments show standard cometary volatiles, including CO2, water vapor, and organic molecules, consistent with natural outgassing. No unusual isotopic ratios, synthetic materials, or energy signatures indicative of advanced technology have been detected. The quasi-living plasma hypothesis ventures even further into speculation, drawing inspiration from laboratory studies of dusty plasmas, where mixtures of charged particles and microscopic solids can self-organize into patterns reminiscent of biological systems. In lab conditions, these plasma formations can reproduce, adapt, and respond to environmental changes in ways that superficially mimic living organisms. Some researchers have suggested that similar plasma behaviors could arise naturally in space, potentially generating phenomena that imitate primitive life. Under this framework, 3I Atlas's anti-tail, brightening, and complex outgassing could reflect manifestations of such plasma-based organization. This concept implies that interstellar space may harbor non-carbon-based forms of self-organization that lie dormant during long interstellar voyages and only activate near stars, producing observable effects that resemble life without true biological function. Yet scaling these effects from lab-sized plasmas to a comet-sized object moving through the solar wind remains purely theoretical. No observational evidence suggests that 3I Atlas exhibits electromagnetic patterns expected from organized plasma on this scale. The purposeful scout narrative imagines 3I Atlas as an active reconnaissance probe from another star system, with intentional behaviors designed to study our solar system. In this speculative scenario, its extensive coma could function as a sensor array or communication network, while the anti-tail might serve as a directional signaling system. Brightening events could represent controlled activation of observation or communication systems timed to coincide with critical survey targets, such as Mars or perihelion. The green hue might signal the awakening of dormant sensors, and rapid brightness variations could be interpreted as data processing or transmission activity. Nonetheless, this hypothesis faces the same evidence-based challenges as the technological beacon idea. Chemical, thermal, and structural observations all conform to expectations for natural, if unusual, cometary behavior. No direct indicators of data processing, directed energy, or technological manipulation have been observed. The exotic matter hypothesis posits that 3I Atlas contains substances or operates according to physical laws currently unknown to science. Theoretical physics allows for possibilities, including dark matter interactions, unusual gravitational effects, or quantum phenomena manifesting on macroscopic scale. Such processes could, in principle, explain unusual anti-tail structures via gravitational anomalies or enhanced outgassing through energy release mechanisms beyond conventional chemistry. Rapid brightening could result from exotic phase transitions or energy storage systems operating under physics not yet discovered. This interpretation frames 3I Atlas as a natural but extraordinary laboratory for exploring physical processes beyond human experience, without invoking artificiality. The temporal anomaly hypothesis ventures into the most speculative territory of all, suggesting that the comet may represent a form of information or matter transfer across time. In science fiction scenarios, 3I Atlas could be a message or artifact sent backward from the future, bypassing conventional causality constraints. Its unusual behavior would then reflect interactions with present-day physics rather than spatial travel between stars. However, this scenario demands physics that not only remains unproven, but fundamentally challenges current principles of causality and thermodynamics. Observational evidence offers no indication that 3I Atlas violates conservation laws or exhibits temporal anomalies beyond standard relativistic effects for high-speed objects. A critical perspective on these exotic ideas highlights a recurring lesson in astronomy. Many apparently inexplicable phenomena eventually find natural explanation. Pulsars, initially considered potential artificial signals, were understood as rapidly rotating neutron stars. Fast radio bursts similarly sparked speculation before being traced to astrophysical sources. Historical precedent suggests that 3I Atlas will ultimately be explained within known physics, even if the processes involved are extreme or previously unobserved. Its unusual properties likely reflect the diversity of environments in other star systems rather than manifestations of exotic matter or technology. The value of entertaining these scenarios lies in emphasizing just how remarkable 3I Atlas is, an object capable of inspiring hypotheses involving alien technology, living plasma, or exotic physics, truly unprecedented among interstellar visitors. As it continues its hidden perihelion passage, these speculative ideas underscore how much remains unknown about the universe beyond our solar system. Whether 3I Atlas re-emerges as a mundane yet unusual comet, or continues displaying extraordinary traits, it has already expanded the boundaries of what is considered possible for interstellar objects. The countdown toward key observational events now begins. Each upcoming milestone will test not only our understanding of 3I Atlas, but also our ability to observe and interpret phenomena at the limits of current astronomical capability. October 3, 2025 marks the comet's closest approach to Mars, approximately 30 million kilometers away. This encounter provides the best chance to maintain continuous monitoring as Earth-based telescopes lose sight. Mars-orbiting spacecraft, despite not being designed for this task, will attempt to capture images and spectra of the rapidly moving interstellar visitor. The outcome depends on factors beyond human control. If the comet maintains its September brightness, these instruments could resolve detailed nuclear structure and coma behavior. If, however, 3I Atlas fades, even the most sensitive sensors may yield only marginal data. Late October brings perihelion, occurring between October 29th and 30th at roughly 1.36 astronomical units from the Sun. During these critical days, radiation exposure will peak, potentially activating volatile stable during interstellar travel, producing outgassing events sufficient to modify the comet's physical characteristics. Unfortunately, perihelion coincides with Earth-based observational limits due to solar glare, leaving maximum activity largely unobserved except through indirect measurement. This observational blackout will persist through early November, encompassing the comet's predicted most active phase, potentially including fragmentation, chemical transformations, or dramatic brightness shift. Re-emergence in early December, as solar elongation increases, represents the next crucial window. The comet that returns to view may differ significantly from its October state, potentially exhibiting fragmentation, altered brightness, or evolved chemistry caused by intense solar heating. Scientific opportunities extend well beyond this period, a close approach to Jupiter in March 2026. Although distant, may allow additional spacecraft observations, depending on orbital alignment and mission readiness. Successful study of 3I Atlas provides far-reaching insight. Analysis of its interstellar composition offers samples from distant stellar systems, revealing conditions in protoplanetary disks across the galaxy. Its CO2-rich composition suggests formation environments unlike the solar nebula, hinting at broader diversity in planetary system chemistry. Observing extreme cometary behavior under intense conditions can refine understanding of volatile release, dust dynamics, and plasma interaction. The anti-tail phenomenon challenges assumptions about comet material responses to solar radiation, potentially demanding new theoretical models incorporating electromagnetic. These observations carry broader implications for interstellar science. 3I Atlas represents only the third confirmed interstellar visitor, yet its unique traits imply that small body diversity across the galaxy is greater than current models predict. Each such object provides essential data for evaluating frequency, composition, and formation processes of interstellar wanderers. Fragmentation during perihelion would offer unprecedented insight into internal structures, exposing compositional layers from different depths, effectively providing core samples from a body formed around another star. Expectation management is essential. Even at peak brightness, the comet will remain beyond naked eye visibility. With estimates near magnitude 11 to 12, accessible only through telescopes. While this limits public spectacle, it does not diminish scientific value. The rarity of such interstellar encounters ensures that every observation contributes meaningfully to understanding both 3I Atlas and the broader population of extrasolar objects. Europe's upcoming Comet Interceptor mission, slated for launch in the late 2020s, represents a bold step toward developing rapid response capabilities for studying newly discovered interstellar objects. Unlike traditional missions, which require years of careful planning for a predetermined target, Comet Interceptor will remain stationed at the Earth-Sun L2 Lagrange point until a suitable visitor appears, at which point it can redirect to intercept and study the object as it passes through our solar system. Yet, even with this flexibility, spacecraft remain constrained by the fundamental challenge of early detection. 3I Atlas, for instance, was discovered mere months before its closest approach to the Sun, leaving insufficient lead time for a dedicated mission, even if rapid response technology were fully operational. Real progress will require detection systems capable of identifying interstellar visitors years before they reach the inner solar system to allow meaningful mission planning and spacecraft encounters. In the nearer term, advancements in ground-based surveys offer immediate promise for expanding interstellar object science. The Vera C. Rubin Observatory, under construction in Chile and expected to begin operations in the mid-2020s, will revolutionize sky monitoring. Its ability to repeatedly image vast swaths of the sky will allow for earlier detection of interstellar visitors, providing astronomers extended observation windows and the opportunity for more detailed study. The Legacy Survey of Space and Time, Rubin Observatory's flagship program, is projected to discover multiple interstellar objects annually once fully operational. This leap in detection frequency will shift interstellar research from sporadic, opportunistic observations to systematic population studies, enabling new insights into galactic small body reservoirs and their chemical evolution. Technological improvements in adaptive optics, high-resolution spectroscopy, and space-based observation platforms continue to expand the frontiers of what can be learned from fast-moving, faint objects like 3I Atlas. Next-generation extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope, promise unprecedented light-gathering power and spatial resolution, potentially transforming how interstellar objects are characterized. The James Webb Space Telescope has already demonstrated the value of space-based infrared capabilities, providing compositional data previously unattainable from Earth. Future dedicated observatories optimized for small body studies could enable continuous monitoring without interference from atmospheric distortion or solar conjunction period. Global collaboration becomes increasingly essential as interstellar object research demands coordinated observations across multiple observatories and time zones. The observational campaign for 3I Atlas has showcased both the potential and challenges of such coordination. Lessons learned from this effort will guide future rapid response campaigns, while data sharing and analysis protocols developed for 3I Atlas, establishing standards for managing high-priority targets that evolve quickly and require immediate global attention. As the rate of interstellar object discoveries increases, these protocols will become indispensable for orchestrating timely and effective observational campaigns. Beyond the technical aspects, the study of 3I Atlas carries profound implications for our understanding of matter and chemistry across the galaxy. Each measurement provides direct evidence of conditions in distant star systems, preserved in pristine form during millions of years of interstellar travel. By analyzing its composition, scientists gain insights into how planetary formation processes vary across diverse stellar environments. Astrobiology considerations naturally emerge. While there is no indication that 3I Atlas harbors living organisms, its complex organic chemistry offers clues about the distribution of carbon-based molecules across interstellar space. Discovering amino acids, nucleic acid bases, or other prebiotic compounds in such objects would significantly deepen understanding of how life's molecular building blocks are dispersed throughout the galaxy. Even without direct evidence of biology, 3I Atlas demonstrates that interstellar objects can preserve intricate molecular structures across vast distances. Planetary defense considerations, although not immediately relevant to 3I Atlas due to its safe trajectory, benefit from these studies. Understanding the behavior of interstellar visitors under solar heating enhances predictive models that could be applied to future objects with trajectories posing potential hazards to Earth. The unusual properties observed in 3I Atlas reveal limitations in current models of cometary behavior, emphasizing the need for planetary defense strategies to consider objects unlike any previously observed in our solar system. Such knowledge could prove vital in assessing genuine impact risks from future interstellar visitors. Public engagement surrounding 3I Atlas underscores both the challenges and rewards of communicating advanced science. Its technical complexity and faintness limit casual interest, yet its interstellar origin and remarkable behavior captivate those attuned to its significance. Educational institutions around the world have integrated 3I Atlas into curricula, enabling students to follow real-time observation campaigns, analyze publicly available data, and witness scientific understanding evolve as new evidence emerges. The commercial space sector is also paying attention, recognizing that techniques developed for studying this comet may advance broader capabilities in small body character, which could prove commercially valuable in the future, even though 3I Atlas itself offers no mining opportunities due to its hyperbolic path. Ultimately, 3I Atlas has already demonstrated that interstellar visitors will continually challenge assumptions about the limits of the universe. Whether its future behavior aligns with current models or presents entirely new puzzles, it has set a new benchmark for unpredictability in astronomical phenomena. The final chapter of its legacy will depend on observations made in the coming critical weeks. Will it reveal itself as a chemical time capsule from another star, a natural laboratory operating under previously unseen conditions, or something even more extraordinary that compels a reassessment of our understanding of interstellar wonder? In the next few weeks, it may flare to unprecedented brightness, fragment into a cascade of debris, or glide silently past the sun, carrying its secrets back into the cosmic void. Whatever occurs, it has the potential to fundamentally reshape how humanity views visitors from other star systems. The call to action for anyone following this cosmic investigation is clear: track image releases from Mars orbiters, including ESA's Mars Express and Trace Gas Orbiter, as well as NASA's Mars Reconnaissance Orbiter, and May. Then watch for post-perihelion updates from the Hubble Space Telescope and James Webb Space Telescope, which may finally reveal the true nature of 3I Atlas. The universe has sent a messenger from another star, and we are on the verge of discovering the message it carries.